Welcome back to, you can say, mechanics and control of robotic manipulator. The last class we gave introduction to motion control. So in that sense, I told like motion control required, or you can say control design required the familiarization of the physical system. Then we can actually like come back to the objective. This is the place where we stopped in the last lecture. So here we are talking about the types. So before talking to the types, I will just give the familiarization part. So for example, I am just saying that, so the familiarization. So okay. So in that case, for example, there is a manipulator. Okay. So I am actually like seeing this manipulator. So I am trying to show something. So this manipulator is having something like free flowing. So in the sense, it is actually like just moving it without doing any task. Okay. So then you can actually like see that this is a different case. Now the same system is having a pin on the bottom. Okay. This is actually like a tracking on the, you can say, screen. Very simple example. Now I am actually like using this pen and touching this, you can say, touch pad. So now if I touch, then only it would be sensing and it will be writing, right? So the same sense, if I think about the manipulator, so then this touching is also important and then following. So then you should know the, you can say, nature of the system, then only you can do it. A very other simple example, you have a laser cutter on the end of the manipulator, or you can say end effector. So it need to actually like cut the you can say metal plank into pieces as per the seam, okay, given. So in that case, the contact of the end effector to the metal piece not at all there. So it would be somewhere away from here, it would be actually like cutting it. So in that case, you can see like the you can say situation for 1 and 2 are completely different. One is actually like the marker you can say tracing on the paper or tracing on the screen. So that is different from the laser tracker following certain path. So that is what I was saying, that the familiarization. So now I hope you are actually like understood that. So now we will actually like move to the broad classification of the robot motion control. So there are two broad classification we used to do. So one is we call motion based, or some people call model free. So where there is no feedback, you can say there is only feedback, so there is no model required, that is what you call model free. So what that means, so you have your robot, okay. So this robot motion, so what you call this is Q and Q dot, so you have taken as a feedback and you do it in a control. So this you will take as a feedback and try to actually like compensate this robot through this mode. So in that case, this is actually like purely based on the motion. So if the motion is actually like giving a exact sensing value, or you can say your sensor, whatever you put it here, the sensor is giving accurate signal, then you will actually like able to follow. However, the problem is, so one is the sensor would be having a noise. Second thing is, usually this motion based control would be having poor tracking performance and as well as sluggish, in the sense, so you have as a step input, so your say you can see controller will take time to reach this. So in the sense, this much time is actually like lag. However, the model base, it will actually like probably go somewhere here. So that is the basic idea between the motion based and the model based. The motion based usually people call model free. So one of the best example for motion based, either you can take a proportional control or proportional derivative control or proportional integral derivative control. Even if it is actually like kinematic level, we can go even proportional integral controls and all. Even the other way around, if we can actually like go simple bang control or simple on off control, which we have used in the olden days AC. So like these all actually like purely based on the motion, okay. So based on the system motion or the feedback, we are actually like trying to control the you can say actuator signal. However, the second method, which is what we call model based, which is definitely efficient and simple. However, the model is actually like inaccurate, so then this will not give a reasonable performance. So that is what we said, that accurate model should be available to do this. So I already told, so we are actually like seamlessly integrating this, and we say that is a hybrid. So we would be doing the motion based control in actually like your hybrid nature, where we try to compensate the model and then we will give the, you can say, feedback base. So that is what the overall idea. So further we want to see what are the other way to classify. So the other way, so most of the assumption which we have done, so either accurate sensing is available, or you can say that the sensor noise is actually like eliminated, or accurate model are available to all of us. So these all actually like the implicit assumption which we have taken for the previous attempt. But the model is actually like not accurately known, or the sensor is having a error. So then how we can do it? So for that we try to come up with two different strategy. So one is what we call robust control, the other one we call adaptive control. So both are actually trying to compensate the, you can say, the perturbation due to, you can say, model uncertainty, or you can say sensing or sensor noises and all. So in that case, so the robust control is, the name itself says robustness. So what that mean? So it is least you can say affect on the external impact. So for example, you are actually like saying that it's supposed to go in straight line, even you disturb in the lateral direction, it actually like least you can say response to that. So that is what you call robustness. So a very simple example I want to give as a, you can say, a layman style. So you imagine, so you all might be knowing like so how to make you can say South Indian idlis. So the idli would be having actually like hemisphere pot. So why the hemisphere is there? Ease of removal. So in the sense least impact on the you can say effort. So when you want to remove that idli from the pot, you can just easily remove it, is because you can say hemisphere. The same philosophy we are trying to give in the robust control. The robust control is actually like more apparently come as the you call high control activity. What that mean? So very simple example we want to give. So you want to compensate probably 10 kg effort, okay. So but you don't know it is actually like 10 kg. So what you will actually like plan, you will plan for probably, so what would be the maximum threshold? So you will plan for 100 kg. So now, so the load is actually like 1 kg or 100 kg, it assumes as a, you can say 100 kg and try to compensate. So in that sense what happened, most of the occasion the high control activity will come. So which means that, so it's supposed to compensate only 10 kg, but it is overwhelming because you are providing more control. So that's why people call robust control more commonly called overwhelming control. So this will be actually like take the effort, but what it does, so even if any small error exists in the, you can say, closed loop, that would be ignored, okay. So in that sense this is actually like what you call robust control. The robust control is more commonly, I already said, it's a overwhelming, or you can say high control activity control. So one of the popular robust control is sliding mode control. So even this robust control have another impact. For example, you assume that 1 millimeter is the threshold, okay. So you assume that plus or minus 1 millimeter is your error limit. So if it is exceed or comes to 1 mm, so what happened, the actuator will start functioning. So you take the air conditioner, so you put 20 degrees Celsius, you assume that it is just a bang control. So now the controller is actually like planned for 20 degree. So your system is actually like reached 20.01. What happened? So your system will start, compressor will start, evaporator will actually like start function, make sure that it comes to 20. So what happened, it may not stop at 20, it may go to 19.99 or something. So then it will stop. So in the sense, if you look at the control sequence, so it would be on, so then off, then on, off, like that it will go. So in the sense, your actuator would be actually like shuttling between one end to another end. So which is what we call chattering. So the chattering effect would be visible in most of the robust control. So that's why the robust control along with chatter free is one additional phenomena people try to do. Even the robust control people try to do with neural network base, or probably you can say matrix base, all those things people tried. So these all we would be discussing in the later part of the class. So the other type of you can say control is what you call adaptive. So in the sense, so whatever the effect due to that disturbance or the uncertainty, that try to compensate directly, in the sense try to calculate what happening due to that uncertainty, how much effort it is deviating, that much effort it would be compensating. For example, so now I assume that the payload is 10 kg, but unknowingly it is actually like 10.5 kg. So now this additional 0.5 kg, how much effort it is actually like produced on your system. So that effort would be calculated and compensated at the actuator level. So this is what we call adaptive control. So the adaptive control more, you can say, beneficial. However, the adaptive law may end up with even the system would be unstable. So because the adaptive control mostly depend on the previous state, the previous state and the current state is having a difference, and the disturbance is fast varying, then the adaptive control may end up with something. And most of the adaptive control would be based on what we call regressor matrix. We'll come back what is regressor matrix. So this regressor matrix usually would be a rectangular. So the rectangular inverse you have to take, and most of the cases the regressor matrix inverse would be more prone to what you call singular. So in the sense the control input would go to probably infinity. So this can happen. So that's why non-regressor matrix, or you can say inverse free adaptive control, all come up in the modern days. So these are the two types of, you can say, control apart from motion based and model based. So here also like it would be combine of model and motion, because the feedback also fed in and as well as model also like incorporated. So these all actually like in addition to that, however, this would be overcome the difficulty which we come across either motion or model based control. So further what we can see, the control scheme can be classified based on where and what way or what level you are trying to implement. So if your controller is actually like implemented at kinematic level, so in the sense you have this equation. So mu dot is j of q into q dot. So I am trying to find out this q dot as the control activity based on my desired, or you can say my position trajectory. I can do it. So then it is a kinematic control. In that case, you have to take it one simple aspect, your inertial effect. So your inertial effect should be so negligible amount. Okay. So here we are neglecting. If the effort is actually like non-negligible amount, so then the kinematic control may not work well. Okay. So for example, you have a planar horizontal robot, okay, that to like slow moving, probably it is rotating probably maximum 1 meter per second is the end effector velocity, then this kinematic level control will work very well. However, if you go for, you can say, high speed or probably a spatial system, so the dynamic control is important. Okay. So then the dynamic control means the robot dynamics also like consider, and the actuator would be consider as per the robot dynamics. Okay. So the earlier case we just bother about only the speed of the actuator, but right now we consider what would be the torque required, how the torque would be obtained from the electrical motor or probably hydraulic motor and all that we will see. Okay. So most commonly people try to combine this kinematic and dynamic, we call cascaded or probably dual loop, where we would be seeing the you can say inner loop would be dynamic level and the outer loop would be kinematic level. Okay. So that is what we call actually like cascaded or dual loop or double loop, which is actually like two stage. So outer loop would be kinematic, based on that the inner loop desired characters will be designed, or you can say defined, then we will actually like do it. So we would be seeing all this detail in upcoming lecture. So we will see what are the other classification can come. So the other classification based on the interest or the application. So whether it is a pure motion or position control, or you want to have pure force control, or it required a combined. For example, now my hand is actually like going to carry a bottle, that bottle is actually like probably a fragile. Okay. So I cannot compress it, right. For example, I am carrying a egg. So then I need to make sure that the position also need to be followed, and as well as the force applied to the end. So that is also important. Then we need to think about the hybrid. So the other way around, for example, your end effector is just pushing it. So for example, there is a conveyor, there is an object. So this object need to be pushed by the end effector, okay, after inspection. So then the force need to be provided in such a way that this would be pushed. So not only the motion, but here at the end the force is sufficient. So then these all actually like come into a classification. But the other, which is actually like a kind of impedance, so the force control also can be brought into impedance and admittance control, okay. But here the impedance, what we are trying to mean that it is something like a teleoperation. So you have a master robot, okay, and a slave robot. So this is actually like smaller size, and it is actually like exact, you can say, replica of the master, you can say slave robot, so to the master. So now in that case, so you need to have a feedback, right? What exactly the original manipulator is doing, that feed you need to have it. So then we will provide the impedance control. So this is most commonly used for teleoperated or haptic device. So that is what we have put it as a separate. So based on the interest or the application, the control can be classified, but this particular course is focused more on position tracking, or we call simply motion control, okay. So further, the you can say control can be classified based on the space which we are using it, okay. So either it can be a joint space, so you are doing entire control activity in a joint space, or you are actually like trying to control the end effector space, so which means task space control. Some, you can say, modern controller come in a sensory task space. So in the sense, so you have a probably camera, the camera is actually like put it on the top, but your manipulator is working somewhere here. So based on this, I can actually like make it all the desired things modified. So then it is actually like what you call sensory task space. So simply people call sensor space control. So olden days we call only task space and joint space. Now modern community brought the sensory task space. So this is one of the important area we can actually like do it. So it is based on which space we consider for the control activity. So further, what we can see, whether you want to control, since we are talking about manipulator, you want to control independent joint, or you can say synchronously with the multiple joint. So these also can become. So independent joint means it's very simple, because you can go with the actuator level, and you can even go with simple PI control, that is sufficient. But if you are thinking about multiple joint control, then we have to depend on further end. That is what we are going to see in upcoming lectures. So further, the controller can be classified based on the nature of the reference, which I already told. One is the regulatory control, which is nothing but the set point. So you have actually like a desired is actually like this is given starting point, and this is the desired. So in the sense, you don't bother about which time it would reach. So in the sense, it is a set point. You need to stay remain after a while. So in the sense, your reference is constant. So this is one subclassification we call set point or regulatory control. Some people even call a stabilization, where from any non-zero initial condition can we come to the home position. That is what we call stabilization. But more commonly we use the tracking. So in the sense, the time, you can say, varying reference input would be given. For example, Q desired is the reference. So this is constant for the set point, okay. So Q desired of time, which is actually like a variable. So this is what we use for the tracking control or servo control, okay. So these are the types. So now we will come back to one concern. With that, we will end this particular lecture. So what is the concern? So you might have actually like heard about PI control in your you can say actuator level. When you talk about DC motor, or you talk about servo motor and all. So one of the standard control is the PI control, but the PI control is not straight away applied to the robotic system, because so the robotic system open loop control is unstable, or you can say open loop system is unstable. The second order dynamics is unstable. So if you apply even PI control, that may not make it stable. It may end up with, you can say, further unstableness. So that's why PI control is not straight away applied. So in that case, what people use, so the PD control. So the PD control is the preferred control on the robotics. So specifically like a dynamic level. So the PI control would be common if we do in a kinematic level, but the kinematic level is not common in robot manipulator community, because so the actuator dynamics and the motion dynamics are actually like not negligible amount. Further, most of the manipulator would be working on multiple body, that too in spatial. Okay. I hope now this is clear. The second part is actually like what is the difference between inverse differential kinematics and the kinematic position control. You already know. So, even you can talk about inverse dynamics and dynamic position control. You know, this is actually like feed forward, in the sense this is a simple open loop, whereas the position control or the motion control which are actually like closed loop. Okay. So, in the sense inverse differential kinematics or inverse dynamics, nothing but it is a feed forward control, where the kinematic or dynamic position control or the feedback control. That is what we should know. So, now I hope you are actually like getting familiarized about what is motion control and what are the types and why PD is required, when we can use PI and when we can use inverse differential kinematics or when we can use you can say closed loop, right. So, these all we have seen. So, in the next class we will see a simple kinematic control. We start from inverse differential kinematics and we end with what you call kinematic control with proportional or proportional integral in the next class. Until then, see you then, bye.